spanning trees. So in the last lecture we discussed Kruskal's algorithm and basically went over how it works. What we didn't do was to give a proof of correctness, so let's do that today. And in order to do the proof, it's useful to talk about some properties of trees. Okay, so one of the properties that's useful is the third bullet here, right? So in a tree, given any two vertices, there is a unique path, right? So what that implies, right, is that if you add another edge to a tree, that will create a cycle, right? Because there is already, let's say this is a tree, and let's take two vertices V and U, right? Because of the property that we already said, there already exists some way, some path to go from V to U. So if you add an edge, right, that's going to complete a cycle, right? So that is what the first bullet says, right? Because it's a structure such that, it's a graph such that if you add even a single edge, right, it's going to have cycles, right? Because the tree is the largest, or it's a maximal in this okay. So it's maximal subgraph without cycles, which means that even if you add even a single edge, then you're going to have a cycle, right? So, and we showed that how from here you could get there, right? Because given this property, right, we showed that addition of even a single edge will cause a cycle to be formed, and therefore it's no longer. So that is another way of saying that the graph is maximal. So you cannot add any more edges. Okay. So what this also tells you is that again, right? So you'll say that it creates not only a cycle, but also it creates a unique cycle, right? Why is it unique? Because let's say you assume that the addition of this edge actually creates two cycles, right? That means, right, so this could be one cycle, and this could be another cycle, right? Which means that there are two ways to get from V to U, right? Which means that there's already a cycle going that way, correct? Is that clear? So when you add this edge, you can create only one cycle, because otherwise, if you said that it is actually creating multiple cycles, right, then it must be the case that there already existed a cycle, and so your original assumption that this was a tree is invalid. Okay, so addition of an edge to a tree creates a unique cycle. Okay, so this is something that we will rely on to prove Kruskal's algorithm, right? So this is the algorithm again, right? It's a very, very simple algorithm. You create a priority queue out of the edges, right? It's organized in terms of increasing edge weight. Okay? So the minimum weight edge is going to be at the top, and the maximum weight is going to appear at the very end. And then you're going to pick these edges one by one, and you're going to add the smallest cost edge or smallest weight edge to your spanning tree, unless its addition will create cycles, right? So its addition will create cycles if it's already connecting. It's already within a connected component, right? So if it's connecting two distinct components, that means there is no other path between the V and U you are connecting, and therefore you will still retain or at least you're towards a tree, right? That is, you're actually you have a forest, right? And then there are no cycles. Okay, so now we want to prove that this actually constructs an optimal or rather minimal spanning tree, right? So so this is what you want to prove. Okay? So just as in the case of the fractional knapsack, we are going to prove essentially using a contradiction, right? So here what we said is we have this switching argument, right? We say, okay, you claim you have the optimal solution, give me that solution. And then I'm going to take that solution, swap out one of your choices with a better choice, right? And that better choice is the one that my greedy algorithm would have made. And this better choice actually results in a solution that's more optimal, right? And therefore, your claim that you had an optimal solution was wrong, right? So that is the proof by contradiction that we have, and it's the same approach we use for proving a number of greedy algorithms, right? So we always going to do this switching out one by the other. So let's see how to do that in the case of spanning tree. Go fast. No? Yeah. Okay, so the argument that we are going to make is so we are going to start with the assumption that, okay, somebody can give me an optimal a minimum spanning tree which has less cost than the one that's built by Kruskal's algorithm, right? So now what we are going to say is that, look, the choice made by Kruskal's algorithm at one step, right? If that choice was not included in this so-called minimum spanning tree, then it actually has a higher cost than what is possible, right? So what we're going to say is, again, okay, give me this minimum spanning tree. I'm going to swap out one of the edges that Kruskal didn't choose with another edge that Kruskal would actually have chosen. I put that in, and now I'm going to show it to you that this new spanning tree actually has a lower cost, right? So this is what I'm going to show. But to prove this gets a bit more involved, because it's difficult to talk about that one edge. So what we're going to do is we're going to say, so keep this in mind, okay, I have to erase it, but this is an important property, right? So which because it creates a unique cycle, right? And a property of a cycle is that you can break any of the edges in the cycle, and that won't affect the connectivity of the remaining structure, right? And therefore, once you break that cycle, if let's say you start from a tree, you add an edge, right? So that'll form a cycle. Now if you break the cycle, right, now you'll have a tree again, right? Because within a cycle, there are two ways to get from between any two vertices. That means you can take out one of the edges and still have that reachability, right? So you will have the property that after creating the cycle, if you break any of the edges of the cycle, you still will have a connected graph, right? And you also have n-1 edges, right? So given all of that, it's pretty clear that you breaking a cycle will get you back to the original tree. It doesn't matter, right? So you could have, let's say V1, let's say V, W, U, right? So you could have had originally these two edges in the tree, right? So then you added V comma U, and then you could erase, let's say, V comma W or W comma U, and still you will have another spanning tree, right? So then that way we can talk about, this is how we are going to talk about swapping, edges. So we are going to say, part of the argument is going to be, let's say this is the minimum spanning tree, right? That somebody was able to construct. So what I'm going to do is, and it doesn't contain an edge, right, V comma U, that Kruskal would have chosen, right? Now I'm going to show you that I can construct a better spanning tree by choosing that edge. And the way I'm going to do that is I'm going to first add this, right? And then I'm going to break one of the other edges, right? And now, again, the intuition is that because Kruskal is always adding the edges in terms of increasing cost, right? If it didn't add this, right, that means the cost of this should have been higher than the cost of this. Therefore, when I add this edge and broke this edge, my overall cost should have become less, right? So this is the crux of the argument as to why Kruskal generates an optimal tree. Okay, so to go through this in a more formal way, what we're going to do is we're going to say, so what we are going to do is, instead of just giving you this example with these three nodes, right? So the more general argument goes like this. So let's take this tree, right? Somebody constructed, which they claim to be a minimum spanning tree, right? So we are going to take that tree, okay, and what we are going to do is we are going to compare the edges in this tree, right, with the edges that were added by the Kruskal's algorithm, right? So what we are going to do is, let's say edges okay, so let's say Kruskal adds edges in this order. Okay? Let's say it adds edges E1, E2, E7, E8. Okay? And let's say E1, E3, and E7 are already there in this so-called optimal tree, right? So what we want is, we want to pick the first edge that Kruskal did not add, right? Which is supposedly in the minimum spanning tree, right? So then what we will be able to say is, let's say, E8 is, let's say E8 is here. Okay? So then what we will be able to show is that, well, when Kruskal decided to add E8, right? At that point, right, these two points were not connected, right? Because only when the two vertices are not connected, it's going to add that, right? So therefore, what you can do is you can add this edge E8, right? And there must at least be one edge along the path from here to here that wasn't there when E8 was added by Kruskal's algorithm. Okay? Let's say that was this edge. Okay? It wasn't already added, right? So the reason why E8 was picked instead of this edge is because E8 had a lower cost than this one, right? And therefore, if I do this switching around, delete this edge and put E8 in, my overall cost would have come down, right? So that's the argument you use for showing that Kruskal in fact builds the optimal tree, right? So it's just this simple swapping argument. So there is a more detailed, argument here, which you can go through on your own. What I want to do is I want to convey the gist of the argument and let you, look through the details. So as we said last time, minimal spanning tree has many applications. Network design is probably the most relatable application, right? So you can see that how if you're trying to build a communication or transportation network, a spanning tree is a good choice because it will make sure that your network is all connected, and the minimum cost nature of it already makes sure that your network, the cost of building your network will be minimized, right? So that's, if you don't remember anything else about MST, right? Remember that, right? So this I don't want any of you to say you took this course if you don't remember this basic application of minimum spanning trees. Okay, now we will now talk about the second example of a greedy algorithm, and this is a shortest path finding algorithm, right? So spanning tree, well, it is about establishing connectivity in a graph, and shortest path is how you get from point A to point B, right? So I suppose I don't have to tell you why shortest path has, or what applications shortest path algorithms have, right? So you're all, if you are first year undergraduates, maybe I have to tell you, but otherwise, I think all of you know enough about the use of shortest path. But the particular shortest path formulation we are going to talk about is called single source shortest paths. That is, you're computing shortest path to every vertex from a starting vertex or source vertex called S. Okay? And the reason why we do single source shortest paths is because the algorithm for finding the shortest path between any two vertices, right? It's about the same as the complexity of finding the shortest path from the source vertex to all the vertices. Okay? So suppose you are asked to find the shortest path between U and B, right? Finding the shortest path between U and B has about the same complexity as finding the shortest path from U to all other vertices. Right? The worst case cost of this problem, right, is no better than the worst case cost of finding a solution for shortest path between just two vertices. So this is why this algorithm called SSP is very commonly used. Okay, so one of the other things to remember is that this algorithm also constructs another kind of a spanning tree, right? It actually constructs another spanning tree, which is called shortest path tree, right? Which consists of all the, which consists of the shortest paths from U to every vertex, right? So that's going to be shown as a tree. And okay, so that's this algorithm. Let's try to understand. Obviously, we have a lot of applications. So the algorithm is actually quite simple. We'll go through here at a high level. So you start with this set called explore, right? So these are the vertices to which you already found the shortest path. Okay. At any point during the algorithm, there are a subset of vertices to which you already computed the shortest path, right? And then you are going to find, essentially each step of the algorithm is concerned with expanding this explored set by one more vertex. Okay? So we have said that there are two properties that you need for applying a greedy algorithm. One is the optimal substructure, right? And the other is a greedy choice. Okay? So optimal substructure is pretty intuitive for shortest path problem, right? So for instance, you can understand that if, let's say, I have a path from U to V, let's say the shortest path from U to V goes through W, right? Then this path going from U to W should itself be the shortest path between U and W, right? So that is the optimal substructure property that we are looking for, right? So the optimal path between U and V is computed by putting together optimal paths that go through some intermediate vertex, right? Or you're not saying that it should always go through the intermediate vertex, but what you're saying is that if it happens to be the optimal path, then every component of it is going to be optimal, right? So it's not that, this is an optimal path from U to V, but for some of the paths, some of the vertices along the way, there is a different shortest path. That's not possible, right? Because if there is a different shortest path, let's say there was an alternate way, let's say this is cost 10, this is cost 8, then of course in this long path, you can swap out the 10 path with 8 path and you'll have a shorter path, and therefore it's not possible. So for every step along the way, you should be having optimal solutions. Okay? So the greedy choice we are going to make is that instead of globally searching and finding the next vertex with the shortest distance or whatever, what we are going to do is we are going to greedily explore just the neighborhood of this explored set. Okay, we're just going to look at the periphery of the explored set, and within that we are going to try to find the next vertex with the shortest path. Okay, why this choice happens to be optimal, we'll come back to that a bit later. Okay, so let's try to understand this high-level view a bit more carefully, right? So let's say at some point in during the algorithm, right? So in the algorithm, we are going to maintain we are going to rely on two quantities. One is distance to u, right? So remember that we are starting with from this vertex S. Dist of u represents the shortest distance we have computed so far, right? We have not yet announced that it is the shortest path to u, but at any point we are going to maintain the shortest distance we have found to a vertex u, right, so far. Okay, and then L of E is the cost of each edge. Okay, once again, the cost can be, sometimes we use the term weight, sometimes we use the term length, and sometimes we use the term cost, right? All of them mean the same thing. Okay, so L of E is because it says length of the edge. I think I use L here because your textbook uses L. Okay, so we said that at the very beginning your explored set is just containing S, right? So now we are looking at some intermediate stage where you have explored some subset of the network, right? So what is the meaning of explored?
You know the shortest path to those nodes in them.
Correct, correct. So I just wanted to remember that by putting something in explore, what we are saying is that we have already computed the shortest path, right? And now what we want to do is we want to figure out what is the next vertex to add. What is the next vertex that we want to move inside this explored region, right? So the claim is it has to be one of the edges that crosses this blue cloud, right? It goes from inside this blue cloud to outside. Okay? Now why? Let's think about the alternative, right? So the alternative is that, well, I guess unfortunately it doesn't even have a good example, but let's say that there is another vertex over here, right? So if you imagine that vertex and let's say you want to say I'm wrong, therefore you're going to say no, this is the one to which I have the shortest path, right? So then the problem is that what you're saying is that So what you're the problem is that if this is going to be shorter, right, then the point to remember is that the distance to this, right, is going to be greater than the distance to this, right? So the point is that, okay, if this was going to be so the point is that before you need to add this to the explored set, you should have added that node to the explored set. Okay? So what that tells you is that it's enough to consider this, right, after one of its neighbors has been added to the explored set. Okay? Let's go through that a bit more carefully. Okay? So what I'm trying to say is, we can draw a different picture to make it easier to understand. So one of the things that we are going to do in this algorithm is we are going to add vertices to this explored set in increasing order of distance. Okay? So that's why we add S first, because S has cost of 0, right? So we add it, and then we are going to look at neighbors of S, and whichever is closest, we are going to add that next, and so on, right? So we're always going to add them in the order of distance. Okay, so what we are saying here is that, let's say this is the explored set. Okay, and let's say it has, right? And let's say if there is a vertex like this, okay? such that it's not connected to anything inside, right? So what we are saying here is that as long as edge weights are positive, right? So let's say this is some C1, this is C2. So if the shortest path to this vertex goes through this vertex, right? Then the cost of going from dist of u, right, is less than or equal to dist of v, right?
Yeah.
Because if C2 is positive, then this distance should be less than or equal to this distance of going from S through U to V. Okay? What that means is that V does not have to be added to this explode set until we have added U to the explode set. Right? So this is why, which basically tells us that we only need to look at the neighbors of the explode set in order to figure out, which one is the lowest, right?
Yeah.
Okay. So now, so this is why the algorithm is like this. So we initialize the distance to infinity for every vertex other than the source, right? Because we still haven't, at the beginning, we haven't computed the distance to any vertex other than the source itself, right? So we're going to set dist S is equal to 0 and dist B equal to infinity for everything else, okay? Now, previous is the field that we are going to use to keep track of the shortest path tree, right? So every vertex is going to have a previous that's going to tell you the tree edge in the shortest path, okay? So we're going to construct a heap because we are going to often interested in the minimum cost thing, and so so what we are going to do is we are going to pick the vertex that has minimum distance from the source vertex S, okay? And then for each so what we are doing here is we are taking the minimum and we are saying now that that is the next lowest, okay? And we are going to move that inside the explode set, okay? And then we are going to go through the edges incident on V, and then we are going to update the distance, right? So what we are doing is that now that we have added V to the explode set, we look at its neighbors, and then we update their closest distance if we need to, okay? Notice that it's not always updated, only if the distance going through V, right, is smaller than the current distance, right? So the known distance to W, you know some value. If that estimate happens to be greater than the distance you achieve by going through V and then taking the edge V, W, now you have found a shorter path. So now you're going to update the distance. Okay? Otherwise, you leave it as it is because this new edge that you're considering is not really part of the shortest path. Okay, and when you do that, to remember that you have chosen this V, W edge, you're going to set previous of W equals V. Okay, so this is how you remember the previous or the edge that is going to be added in the shortest path tree. Notice that this could be updated multiple times, right? Because you could have multiple edges into W, and you might update, the cost multiple times, and each time you might set this to point to a different V. Okay? And once you have done that, if the distance estimate actually decreased, then you need to adjust the heap, right? Because the heap needs to have return the elements in increasing order. So if one of the keys has decreased in value, you need to adjust the heap, right? So this is, as we know, takes logarithmic time, right? So adjusting a heap takes logarithmic time. Okay, let's look at this example to understand how the algorithm works. So you start with A, right? So A is the source vertex, so you start with that. Okay, and then you're going to initialize.
We initialize everything to infinity.
Right, so initially for each vertex, so A is going to have a cost of 0, everything else is going to have a cost of infinity, right? So now you go through, you're going to do so you're going to delete the minimum from the queue because S is the only one that has a 0 cost. So the minimum is going to be S. So you're going to pick, delete S from there, and then you're going to update the cost of the neighbors of S, right? So that's what we do here, right? So whatever element is deleted, its neighbors, their costs are updated, right? If necessary. So what we're going to do in this case is we are going to take A, look at its neighbors, and update their costs, right? In this case, because their original costs were all infinity, so it's going to be updated. So that's why you have B having a cost of 4 and C having a cost of 2, right? And A does not have any more neighbors, so the other costs are not updated, right? So now what you're going to do is after updating the cost, you're going to go back to the loop and ask for delete min, right? Now, in this grouping, A is no longer there in the queue, so the minimum is going to be C, okay? So C is going to be added to the explore, which is this dotted line shows what is explored. So you have C, and then you're going to look at the neighbors of C, and then update their cost, right? So C has an edge to B, okay? So now that path,
2 plus 1.
so the cost of C is 2, so plus this edge is 1, so you have a cost, you have a distance to B that is 3, less than the original distance 4, so you update that, okay? So then now you also are able to reach D and E, so their costs get reduced from infinity to 4 and
7, 6 and
6 and
7.
7.
2, A, C, C.
Yeah, right, I'm sorry, yeah, you're right. So 2 plus 4, 6, and 2 plus 5, 7, right? So right. So then, now we ask for the minimum again. Now you see that A and C are no longer in the queue, so B is going to be picked, right? So, and then we do the same thing, and you can see B has 2 edges, right? B to D, that gives you a path of distance to B is 3, 3 plus 2, 5, right? And then you have a distance to E, which is 3 plus 3, 6, right? So those costs get updated, and you also expanded the set to include B. Now you look for the minimum between D and E, right? E is the D is the minimum, and so you look at D, and then well D actually does not even have any outgoing edges, and then you're done. So by the way, spanning trees we said, right, are the spanning tree algorithm is carried out on a undirected graph, right? Whereas shortest path, you can talk about it either on directed or undirected graphs, right? And it doesn't really change the algorithm in any way, right? So you can, or in other words, it works on undirected, directed graphs, and you can think of undirected graph is a special case where the edges, where each edge is, duplicated once in forward direction and once in backward direction with the same cost, right? So in that sense.
Professor, this is the example that you mentioned that if there is some vertex that we don't explore,
Yeah.
then if we don't consider it, it is fine because an edge from E to D will only be more than we already know that D is 5, so there's no need to explore E.
Right.
Because any edge from E will only add.
Correct. So you don't have to look at, you could add, if you go to the very last step, you will add E to the explored set, right? But then at that point, because it's the last vertex being added, there actually cannot be anything more, whose distance is going to be reduced. Okay, yeah.
Are there any optimizations in choosing the correct start node?
Correct start node? No. That's part of the problem, right? You want to compute distance from a start node that is specified to you, right? So that's part of the problem. You cannot. So let's look at the complexity of the algorithm. Well, now, okay, maybe we should look at the. So let's look at the runtime, right? Correctness uses the same, switching type of argument. I'm not going to go through it, okay? At least not right now. So we will revisit this algorithm again sometime in a few lectures, along with a number of other shortest path algorithms. And at that time, we will have a more general discussion of correctness. Okay. So runtime. So delete min is going to be called v times, right? And because the heap contains the vertices, so the delete min, all the delete min operations together are going to cost v log v time, right? The inner loop, right? So we go through V and we go through the edges that are incident on V, right? So this nested loop, right, is going to be the inner, the body of the inner loop in this nested loop structure is going to be executed exactly E times, right? Because it's going to be executed once for each edge, right? So that's why the inner loop executes order of E times, and each iteration takes O of log V because we have to do this decrease key, right? The decrease key is log V cost, so you're going to do O of log V. So you have the total time of E plus V log V, okay? But of course, generally speaking, you're probably not going to do single source shortest path in a disconnected graph. So if you're talking about connected graph, E will always be bigger than V, right? So then you can say E log V is the complexity of this algorithm. Okay, E log V, which if you can think about it, right, seems quite efficient, right? I mean, you think about if you didn't know anything about shortest path algorithms, and you're asked to find the shortest path from one source to every destination in the graph, right? Of course, you're going to spend, E time because you probably have to look at every edge. But to only have a factor of log V after that, right? That is quite remarkable, right? So it's actually a surprisingly efficient algorithm, right? Again, keep in mind, right, the argument we made, right, about why it's enough to look at the neighbors of vertices here, right, is based